Hello everyone, this is Dilip. Today we'll talk about convergence in gradient descent. Convergence in gradient descent. So what is convergence? Convergence means the point where the cost function value becomes minimum. Now in gradient descent, our goal is to approach the convergence point for the cost function as quickly as possible. So this will reduce the impact on computing resources. Now, for example, consider there is no bias parameter and we have only theta1 and theta2 representing two variables, which is size of the house in square feet and number of bedrooms. And if we take the same range of values, where size of the house is in thousands and number of bedrooms is normal between 1 to 10, we will get the cost function like this. It will be very skewed. Pattern drawing, but it will be very skewed. So if you want to go about gradient descent on this skewed cost function, it will be very slow. And it might even sometimes go in wrong directions as well. But if you scale the parameters such that both size of the house and number of bedrooms is in between 1 to 10, your cost function will give us nice circles. So the contours will be nice circles. They won't be skewed and it will be good for gradient descent as well. And suppose you start at a point here, you can quickly go for convergence. So it is important in gradient descent or any other machine learning algorithm you will see in the later videos to scale down the parameters such that, not parameters, variables in the test data such that all of them are in a similar range. So to reduce the parameters, there are two main techniques. The first one is called feature scaling, where we rescale the parameters by dividing or multiplying them. For example, if we have the size of the house as seen in last slide in 1000, 2000, 3000, and if you want to reduce their size and have them similar range between 1 to 10 like number of bedrooms, we can just divide them by 1000. So having the variables in a range between -1 to +1 is good, but it's also okay to have between -9 to +9 or similar range. And if we have one set of variables in between 1 to 10 and another set of variables in say 10,000, 20,000, that is not okay. In the same manner, if we have one set of variables between 1 to 10 and another set of variables in microsecond or millisecond, so that is also not okay. So just make sure to put the variables at max a multiple of 10. So if you have between say -0.1, -0.01 to +10, that is also okay. Okay. So try to put them within a particular range and try not to go too small and try not to go too big. If they're too big, divide them. If they're too small, multiply them. Now let's go to the next slide. The second way to tone down the variable size is mean normalization. So in mean normalization, we replace the feature xi with xi minus mu I by si. So which will result in approximately zero mean. So usually this will result in variable sizes ranging between -0.5 to +0.5. So here Let's take an example to explain this. Say you have size of the houses given like this in the test data. Now we take the average of all these values. It will be adding all of them divided by 4. So this will result in, sorry, 4. Okay. So this will result in mu I, which is the average, which is a mean, which is 2375. Now the denominator is standard deviation. The standard deviation is nothing but the difference between the minimum value and maximum value, and this is 2500. So this will give us the range of values which have 0 mean. So this is another way, but most of the time the feature scaling is the one which is used. Now feature scaling and mean normalization, they are one thing, like they will help gradient descent proceed faster, but when to stop the gradient descent? So in the previous video we have seen we get a cost function. As an example, we have taken the cost function approaching 0, but not always the cost function approaches 0. So usually people tell it to stop the cost function when it becomes to the order of 10 to the power of -3, but better to not fix any fixed convergence point. Just plot the graph and as a function of number of iterations, and you will see when the cost function has flattened out, and then you can stop. And the other way is, like, you can see the difference between the cost function between the previous iteration and the current iteration. If it has flattened out, then you can stop the iterations for convergence. So a normal cost function plot, if the gradient descent algorithm is written properly, it will result in the cost function going down with the number of iterations like this. It will flatten out at some point. But if our gradient descent, whatever we have written, the code is wrong, it might result in the cost function going like this, or the cost function going like this. So this plotting this graph helps us in 2 ways. One is to get to the stopping point of convergence. The second one is whether our gradient descent algorithm which you have implemented is correct or not. Okay. Thanks everyone for listening. If you got any good information from this video, please like, share, and subscribe. Thank you everyone.